What is up, you guys? It's your teacher back with another video. So without any further trouble, you've seen the title of the video, so let's get right into it. Question number 1 says, a student conducted an experiment to investigate the reaction between calcium carbonate and dilute nitric acid. He weighed 1.8 grams of powder calcium carbonate and allowed it to react with excess dilute nitric acid. And the volume of gas produced at 10-second intervals was measured for a total of 80 seconds. Table 1 is a record of the volume of gas produced from the reaction. Figure 1 is an incomplete diagram of the arrangement of the apparatus used in the experiment. All right, so here we have our table. Later on, we're going to be plotting a graph from that information. Okay, so question 1A. Now some of the items you're going to see it has been done already, just for the interest of time. So we have the apparatus. As you can see, this is what CXC had provided with us already, and I've already went ahead and drawn the what is extra. So here we have the delivery tube, the rubber bung, and the delivery tube. We find it in a trough of water and an inverted measuring cylinder and a clamp to hold it in place. So as the reaction goes on, we expect some gas to enter the delivery tube, and it's going to displace some of the water in the measuring cylinder, and whatever is displaced, that is the amount of gas that was collected for the experiment. All right. So there we have it. And I am not much of an artist, so I provided you guys with another diagram for you to see, just in case my one wasn't so clear. All right, moving along. So now we are going to move on to plotting the graph. Now, using the axis in figure 8, plot a graph on page 5 showing the volume of gas produced versus time for the reaction of dilute nitric acid with a powdered calcium carbonate label, and we're going to label that graph A. All right, so here we have it. This is our graph. They have already labeled the axes for us to save us the time from trying to figure out a scale. So here we have graph A, and we can see the shape of the graph. I was able to plot this before starting the video. All right, and you can see we have another line called graph B. So that's for us to look at a little bit later. All right, so question C asks us to write a balanced equation including state symbols for the reaction between calcium carbonate and dilute nitric acid. So first, let us go ahead and draw out or write out our reactants. Here we go. So we have calcium carbonate, all right, and we know that is a solid. We have nitric acid, and that's definitely going to be in aqueous solution. Then we have calcium nitrate. So the reaction produces calcium nitrate. All right. And we have the gas, carbon dioxide, and H2O, which is liquid. All right, moving along to question D. And it asks us to calculate the volume of gas that can be obtained from reacting with 1.8 grams of calcium carbonate with dilute nitric acid at RTP. All right, so for this question, we're going to be using the concept of proportionality. So the question already told us that 100 grams of calcium carbonate is 24,000 centimeters cube. All right, so we're going to say 100 grams of calcium carbonate is 24,000 centimeters cube. But how did we get the 100 grams of calcium carbonate? Remember, they provided us with the relative atomic mass of each of the atoms present in calcium carbonate. And if we were to add up all of those, so we'd have 16 times 3, that's the amount of oxygens. We have 1 carbon. All right, we also have 1 calcium, and that will be 40. And if we were to add up all of those, we are supposed to get 100 grams. So there we have it. Now let's go back again. So we said 100 grams of calcium carbonate is equal to 24,000 centimeters cube. All right. So we already have this done. We already know that 100 grams of this gives us 24,000 centimeters cube of carbon dioxide. Now we want to know, what if we had 1.8 grams of calcium carbonate? What volume of carbon dioxide would that produce for us? So in that position, we're going to put X. All right. So now we're just going to cross multiply. We just cross multiply. So on the left hand side, we have 100 grams times X. All right. And we have on the right hand side, we have 1.8 grams times 24,000 centimeters cube. All right, but we're still in a problem here. We have not moved the X, or we don't have the X by itself as yet. So our next step is to move the 100 grams over to the right hand side, and it is currently being held in place by a multiplication sign. And the opposite of multiplication is division, so we have to divide both sides by 100 to get rid of the 100 from beside the X. All right, so we cross out that, and now we are left with X is equal to 1.8 grams times 24,000 centimeters cube over 100. And our answer, I did some of the calculations beforehand. So X is equal to 432 centimeters cube of carbon dioxide. Easy. Moving on. So question E is asking us that from the graph, the total volume of gas produced is 360 centimeters cube, and we're going to calculate the difference in volume between the answers obtained in D and the total volume produced. So we want to suggest a possible reason for the difference. So and remember difference, what does difference mean? Difference is subtraction. So we're going to take 360 centimeters cube, which is what the amount of gas produced that we saw from our graph, and take that from the answer that we got from our answer in D. So 432, all right? So 432 centimeters cube minus 360 centimeters cube. And our answer here, and the difference is 72 centimeters cube, all right? So the answer that we got here, the reason, and that is really one of the reasons why we tend to plot graphs alongside the experiment to see how far off we might have been from the true value. Now, the reason that we're going to use for our answer is that there might have been impurities in the sample. So there might have been impurities in our sample. All right. Now, question F. What are the three factors that can affect the rate of reaction between dilute nitric acid and calcium carbonate? Okay. Now, when we're thinking about the factors, always remember that these factors, they help to increase the likelihood of a collision for a reaction to take place. And these are, we have surface area. All right. We have concentration. And the last thing we have here is temperature. All right. Moving along. Question G. All right. Now, if marble chips, large granules of calcium carbonate, were used instead of powdered calcium carbonate, sketch a graph of what this reaction would be on figure 2 on page 5. And they're asking us to label this sketch graph B. Now remember, I had already put on graph B for us. So they want us to draw a second line and to see what it would look like if we use marble chips, all right, instead of powdered calcium carbonate. And this is what it looks like. We basically have a straight line and it tapers off same way at 360 centimeters cube, all right. So that's what we have there. So the question G is done. All right. So question H Complete the table below by identifying one similarity and one difference between graph A and B and suggest one reason for each. So in terms of similarities, both lines stabilize at around 350 centimeters cube of 30. So both lines stabilize at around 350 centimeters cube of carbon dioxide produced. And the reason here is because there is equal mass of calcium carbonate used in each reaction. So it doesn't matter the state of the solid, right? We're gonna still get the same amount of carbon dioxide here. All right. And the difference here is that line A's slope is going to be steeper than line B's. The reason being is because the powdered calcium carbonate was faster because there's a larger surface area which increases the chance of collision. All right. So the state will have something to do with the collision rate, which will then in turn make the reaction move a bit faster. Okay, moving right along. So question 2. Now, Kwesi went to the kitchen to collect his morning snack during his study break and saw some strips of green pepper in a container. He did not think anything of it. But when he returned to the kitchen table or the kitchen later, he observed that all the strips were swollen. And he said, this must be osmosis, he thought. All right, so question 2I, it wants us to define the term osmosis. And simply put, the term osmosis, it is just the movement of water, all right, of water molecules from an area of high concentration to an area of low concentration through a selectively permeable membrane until it is evenly distributed. All right, and 2I, AI, it's now asking us to explain how osmosis in the pepper supports the particulate theory of matter. All right, so here, the strips become swollen in the solution. Because the solution is hypertonic when compared to the pepper strips. So therefore, the water particles now, all right, and that is our answer. So, and it makes sense, right? Because hypertonicity is when the solution is of a lower concentration than what is inside of the cell. So students, as you can see, the sciences are all interconnected. So please do not study in isolation because this is a concept you would have learned in biology. So in answering the question, bear in mind that the arrangement of particles dictates its shape as well as its properties. All right. Question 2A3, the green pepper was a solid and that was placed into a liquid. And we're asked to state how the arrangement of particles in a liquid differs from that in a solid and a gas. All right. So bear in mind in this question that the arrangement of particles is going to dictate its shape as well as its properties. All right. So in a solid, the particles, they have no space between them. So in a solid, the particles, they have no space between them, and it is normally a regular arrangement. And a liquid is randomly arranged. The particles, they tend to slide relative to each other with slightly smaller spaces in between them. And a gas, on the other hand, the particles have no arrangement with larger spaces between them. Okay, moving on to question 5. Diffusion is another process that supports the particulate theory of matter. State one example of such a process, right? This one doesn't need much explanation. KFC or Burger King from across the road, and you can write that in your exam and you get your marks. KFC or Burger King from across the road. So that in itself explains diffusion. How come KFC is over here and you way across the road can smell it from all the way over there. All right. And you can also think of some similar examples, right? You leave an air freshener in the corner of your room, and when you come back, the whole room smells so wonderful. Think of all of those things when you are doing your exams. Okay, question B. The element chlorine has an atomic number of 17, and it has two main isotopes with mass numbers 35 and 37 respectively. All right. Now question I says define the term atomic number and mass number. So remember, an atomic number of an element is determined by the number of protons in it. All right. We use this to differentiate one element from another. All right. The mass number of an element is determined by the total number of protons and neutrons. All right. Question 2 says that to show by calculation that chlorine 35 and chlorine 37 are isotopes. All right. So chlorine 35 and chlorine 37 are isotopes. So here we have 35. So chlorine 35. So remember that they are both isotopes. So 35, which is the mass number, all right, and the number of protons, which for chlorine is going to be 17, and for chlorine 37 is the same also. So the number of neutrons we have in each, they are going to be different, right? So 18 neutrons. Here we go. All right, so moving right along. So we have question 3. So throughout a student while investigating the reaction of chlorine bubbles chlorine gas into an aqueous solution of potassium iodide and deduces that the potassium iodide was oxidized because a color change occurred. Now we're asked to write a balanced chemical ionic equation with state symbols for the reaction that is responsible for the color change. So now guys, in this particular question, we're asked to write an ionic equation. As you know, an ionic equation only shows the ions that are participating within that specific reaction. All right. Now the steps are as follows. Now the steps are as follows, guys. So the first thing that we want to do, we want to write the chemical formula just as you normally do. So in our case here, we have chlorine or chlorine gas, all right, and we have the potassium iodide, okay, which becomes potassium chloride, aqueous, okay, and iodine has been displaced in the solution, all right. Now, step number 2 asks us to take apart the ionic compounds. Okay, so we're going to dissociate them. We're going to take them apart into their dissociated ions. Now, chlorine. All right, so chlorine is still by itself. It is still a gas. So we have the potassium here. All right, and plus 2. All right, 2 iodides, same here, plus 2 calciums, okay, plus the iodine, all right. So those are aqueous, all right. Now the next step here is we're going to look on both sides of the equation and we're going to cross out what some of the things that we see in common. What are the ions that we see in common on both sides of the reaction? All right. So here we go. I'm going to do this in red. So we see two potassiums on each side. So we cross that out. We see 2 iodides. Sorry. All right. So the common ions. Okay, so step 3 asks us to look on both sides of the equation and cross out the common ions, right? So the common ions, those are the ones that are the spectators, meaning that they're not doing anything special in the reaction, right? So we're going to cross them out for the purpose of our ionic equation. Look on both sides of the equation and we see 2 potassium ions. So we cross those out. All right, we won't be needing those. All right, so moving right along. So our answer here, or the ionic equation. So we just pull everything together. All right, and that will give us our answer. So we have the chlorine and we have the iodide ions. All right. And that is what we get. So let us also assign some charges too. So the charge of the chlorine is 0. We have 2 iodides there, so we have a charge of -2. Same here with the chloride ions, and iodine is in its elemental form, so that is 0 as well. All right, so there we have our ionic equation. All right, a little organic chemistry. Now, compound A is a straight chain hydrocarbon with a molecular formula C5H12. And we want to state 1 natural source and 2 uses of compound A. Now, the source here is actually petroleum. So let's write that. So petroleum. All right, and the uses for petroleum, we have quite a few, because remember, petroleum is used in the cracking process, and its compounds, they have different uses and many different properties. So we have the solvent and we have the fuel, all right, and it can be used for polystyrene foam production. So those are some uses of petroleum, right, in its raw form, right? In its raw form production. There we go. And just to save the instance for the interest of time, they wanted to draw the structure of the compound A. All right, and here we have C5H12, and as we know that this would be pentane, right? It has no double bond, so therefore this one is pentane. Now, question B says, thermal and catalytic cracking are very useful processes in the petrochemical industry. All right. Now, question 1 says, define the term catalytic cracking. All right. And it's the process of breaking down complex hydrocarbons into simple molecules using a finely divided solid catalyst. All right. And question 2 is asking us to state the importance of catalytic cracking in the petroleum refineries. All right, so using a catalyst, and I think they're also asking us to kind of draw a comparison between thermal cracking and catalytic cracking, all right? Because when we're using a catalytic instead of a thermal cracking method, the process can be done at a lower temperature and pressure, right? Under lower temperature and pressure conditions, right? So therefore, it's more energy efficient. Remember, that is the whole job of catalysts. Catalysts are there to lower the activation energy of the reaction, so that the lower temperature, right? The lower temperature and pressure, that checks out. Okay? So since they lower the activation energy, it makes the reaction happen faster and it is more energy efficient. Moving right along, question C. Ethene undergoes a halogenation reaction to form dichloroethane, 1,2-dichloroethane. We're going to draw the fully displayed structure of 1,2-dichloroethane. All right, so here we go. We're going to draw the structure here for dichloroethane. Dichloromethane can be obtained from methane. This reaction takes place in 2 steps, and they want us to write a balanced chemical equation to show each step in the formation of dichloromethane. All right, so question D says that dichloromethane can be obtained from methane, and this reaction takes place in 2 steps. Now, DI says write a balanced chemical equation to show each step in the formation of dichloromethane, right? So this is a substitution reaction. I gave the answer away for the next question, but anyway, knowing this from earlier on is going to help you in writing your chemical equation. All right, so the chain is actually initiated by UV light breaking a chlorine molecule into free radicals, and these are the reactions which keep the chain going. All right, and we're not going to show any radicals, we just want to show at what point are we going to get dichloromethane, and the reaction could actually continue until all of the chlorine molecules, until all the hydrogen atoms have been substituted for chlorine atoms. So the reaction could have continued until we get tetrachloromethane. All right, but the question is interested in dichloromethane, so we're going to go ahead with that. So first, we're going to start out with CH4, and that is our gas. All right, and then we have our chlorine gas. All right, and the UV light, as we said, is what turns these chlorine atoms into radicals. All right, the next step in the process, is going to require us to use this byproduct here. All right, so the next step of the process actually uses this byproduct. All right, this is the important product that we're going to use. So we have CH3, all right, some monochloromethane. All right, then we come again with another chloride, right, molecule, another chloride, a chlorine gas, sorry, and UV light initiates another chain reaction. Okay, so our answer is almost finished. Here we have CHCl2, CHCl2, all right, plus HCl, our hydrogen chloride gas. And there we have our answer. Okay, now question 2, we already gave away the answer, right? If state whether the halogenation of methane is an addition or a substitution reaction, right? And of course the answer is substitution, because at each turn of the reaction another chlorine is substituted until there are no more spaces left on those carbons. And remember, the question says that this is a halogenation reaction. So if they ask for a bromination or an iodination, remember that they are all halogens. Do not be alarmed, just do the same thing that you saw here. Okay, moving right along. We're on the home stretch, guys. We're on the home stretch. And if you haven't already, please go ahead and like the video and subscribe so that you can see more content as it comes out on this channel. Question 4. Now, the position of an element, unknown element Q, is shown in the periodic table in figure 3. Question 4i wants us to state 2 factors that are used to arrange the elements in the periodic table, right? Now, what are the 2 factors that can be used to arrange the elements in the periodic table? We have the number of protons. So the number of protons, okay, in the nucleus, and that is the atomic number, okay, as well as the number of electrons in the outer energy level, which is the valence electrons. All right, so that's 1, and the number of electrons let me just, for shorthand, we'll just say in the valence shell. All right, moving right along. Question A2, based on the position of element Q in the periodic table, state whether it would react more vigorously or less vigorously with water than magnesium. Now, right here, it would react more vigorously. So it would react more. So it would react more vigorously. All right, and why is that so? All right, so it would react more vigorously with water than magnesium. Why is that? Because Q, it actually has an extra shell because it is in period 3. All right, and elements on that side of the periodic table, it is easier for them to lose electrons than it is for them to gain electrons. So it then means that the ones here, they are most reactive when their valence shells are further away from the nucleus, right? So they are able to lose electrons the easiest, so therefore they're going to try to lose electrons as quick as possible so that they can obtain the noble gas configuration, right? That is why elements, they either want to share electrons or they want to give away electrons just for them to become stable and have the noble gas configuration, all right? Now, question 3, state whether the solution formed from the reaction of Q with water would be acidic or basic. And they want to give a range on the pH scale in which the solution would occur. All right. Now, the answer here will be basic. Right? So that gives you your first mark. And the range on the pH scale that would occur would most likely be within the range of 10 to 12. Remember that there are different definitions for acids and bases, and you must be aware of them, right? This question is mostly about electron donation, so therefore, the Lewis acid and base definition would most likely fit here for it to apply, right? So the Lewis acid and base refers to the donation of or acceptance of an electron pair. Remember, Lewis bases donate an electron pair, and Lewis acids, they accept an electron pair, right? So a better Lewis base would be one that would be able to give away its electrons easier, right? And therefore, the atoms that have their valence shell further away from the nucleus, that means that they would give away their electrons much more easier. Therefore, they would be better Lewis bases. I hope that helped. So, question 4, based on the position of element Q, write the formula for its carbonate. All right. So we want to write the formula for the carbonate. We could simply do it shorthand as well, because we have gotten to that point already. But let us do the long way so that we all can understand what is going on. So element Q. All right. Let's see if I can find a nice little space here. Okay. So Q. All right. Now, Q is in group 2, and elements that are in group 2, they have a +2 charge, all right? Calcium carbonate, we know, has a charge of what? -2, all right? Now, they always say that when two atoms or molecules, they have similar charges, or they have the same face value of charges, then all we have to do is just cancel out the charges and we put them together. So there we have calcium carbonate. So their charges basically balance out each other. So Q carbonate. All right. So that would be our formula there. But you can just write Q carbonate right here. You don't need to show the working out, because I think at this point the examiners would have, you would be able to do this in your head by now. All right, so question B, the answer here, right? The answer here is just going to be ionic, right? So remember that elements that are further away from each other, right, they tend to form ionic bonds, right? So the difference in electronegativity is too great, and as a result, the ones with the higher electronegativities, they are going to be able to they're going to be able to take the electron for itself, but this in itself, it creates a charge between them. So they're still stuck together. State the appearance that sodium chloride is expected to have, right? We all know what salt looks like, I hope, right? It's a white crystalline solid. There we go. Question C. Carbon is a non-metal element that is group 4, that is in group 4, and it exists in 2 forms, and those are diamond and graphite. Okay? Now, which of these forms conducts electricity? And I hope you guys have the same answer that I have in my head. And the answer here would be graphite. Why is that? C of electron. Does that ring a bell? Diamond has all its valence electrons filled, right? Bonded. But graphite, each carbon atom is only bonded to 3 other atoms. And if you remember, carbon has 4 valence electrons. Therefore, one is free to move about as it pleases. So we have a sea of electrons free to do as they please, and therefore that means that they can conduct electricity. All right. All right, so here are the structures below as we had. Here we go. So question 2, show by using diagrams the difference in structure between diamond and graphite, which accounts for their difference in conductivity, right? As we just spoke about. So use solid lines to show strong bonds and dotted lines to show weak bonds, all right? So diamond here, I have, as I said, I would have drawn some things just to save time. Diamond here, we see the strong covalent bonds. Each bond is covalent, and that's why diamond is so hard to break, right? And that is also why they put diamond on the end of drill bits, because diamond is so hard to break. It's a very hard substance. They even use diamond to cut diamond. And we also have graphite. Some of my artistic skills are coming to light. All right, so graphite, this is what it looks like. We have a hexagonal arrangement. I hope I got my polygons correct. So what happens with graphite? We have 2 layers of graphite, all right? 2 layers of graphite, and in between them we have these weak bonds, and the van der Waals forces, yes. Between them, all right? And in between them, right, we have the sea of electrons around them, which is what creates or allows it to conduct electricity. All right, so those are the 2 structures there, and ensure that you guys know what to draw when you go into your exams. Moving right along, now question 5A. 5A, the fully displayed structure of compound BC4H8 is shown in figure 8. Now what is deduce a homologous series to which compound B belongs. Each homologous series has a functional group, right, that places it within that series, right? Sometimes how I like to think of it is that I look at the compound and I use an alkane as my reference point, which has no double bonds, nothing at all, just regular carbons. So what looks like it shouldn't be there, right, is normally the series that it belongs to. I hope that makes sense. So if there's a double bond there, it's definitely an alkene. If you say a triple bond, it's definitely a alkyne, right? If we see an OH group somewhere, right, we know that it is a alcohol. If we see a carboxyl group, then we definitely know that it is a carboxylic acid, right? I hope you guys get the point. All right, so this right here is an alkene. So that is an alkene. And what is the name of this compound? It's butene. And if we want to get specific with the proper naming conventions, we can say butene, because the double bond is at the first carbon. And remember, when we're doing naming, the functional group or whatever it is given the lowest number carbon. All right. Now, question 3: what is a structural isomer? Define the term structural isomerism. Now, the compound has the same molecular formula, right? But the way in which the atoms are arranged in space, right? So same molecular formula, different arrangement of atoms in space, and I'll just write that. So same molecular formula. All right. Different arrangement of atoms in space. All right, but different. Let me just put the but right there. Okay, so question 4: draw the fully displayed structure of any structural isomer of the compound B and name it. All right, so I chose butene. So all I did was move the double bond from the first carbon to the second carbon, and that right there's another isomer. So we change the arrangement of the atoms, right? And it's the same chemical formula, right? But the structural formula is different. So we have but2ene. So the question says, we want to draw the fully displayed structure of any structural isomer of compound B and name it. Now, we have but2ene. So already, guys, we have but2ene. So it wouldn't hurt to add another one to it. Now, the other structural isomer that we have of but1ene, right, is 2-methylprop1ene. Okay, so hopefully it's going to make some amount of sense. So here, let me just rub this out. So basically what we want to do here, so we are going to move this methyl group over here, all right, and then we're going to put it over there, and this hydrogen atom, right, is going to take its place and it's going to set itself right there. Hopefully that makes some sense. So let's make it make sense now. So here we have, so we go ahead. So remember we said that the base or the main chain is basically a propene. All right. So we draw our CH2, we add our double bond. All right. Single bond there. Remember we said the methyl group is going to go here, right, on the second carbon there. And we have, there we go, the hydrogen atom. All right, let me just do it in a different color, just so that we remember where it was coming from. Okay, so there we have it. So we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogen atoms, 4 carbon atoms. So therefore all atoms are accounted for. So here we have 2-methyl, okay, prop 1-ene. All right. So there we go. That is another structural isomer of but1ene. There we have it. Moving right along, folks. So we have in question B, ethene and propene are typical monomers which are used as starting material for making polymers. In forming polymers, ethene and propene, they undergo addition, polymerization, and they're asking us in question I, all right, to define what a polymer is. And a polymer is really just a large molecule that is made from the joining together of smaller repeating monomeric units. So in short, it is a large molecule. It's a large molecule made from joining smaller monomeric units. All right, and what is addition, polymerization? And also, guys, pay attention to the weighting of marks in the exam. So here we have only 1 mark allotted for these questions. So you don't have to write an extravagant explanation, right? So these markings are also there to help save you time as well, so you don't spend too much time on one question. All right. Addition, polymerization, and that is just a chain reaction that adds the same monomeric unit to the growing polymer molecule, one at a time, through the use of double or triple bonds in the monomer, right? So remember, the double or triple bonds, those are electron-rich regions, all right? So that means that other atoms, they can come and occupy spaces on that double bond. State one use of the following polymers. We have polyvinyl chloride and we have Teflon. So one use each. I'm just going to add a few more just for the variety. We have pipes, we have fittings. All right, so question C. There are several different types of polymers. Figure 5 and 6 below show the partial structure of a polymer. Deduce the type of polymer shown and the type of polymerization reaction that took place in each case. All right, so the type of polymer here, guys, is actually a polyamide. All right, that's actually a polyamide, and the bond, right? Polyamide, and the bond between the repeating units. Where have we seen it, guys? Where have we seen this bond before? Where have we seen it? Come on, where have we seen it? That's right, the synthesis of proteins. That right, there's a polymerization reaction, okay? And what type of polymerization is this, right? What type of polymerization is this? And that segues nicely into the next question, right? This is actually a condensation reaction. This is actually a condensation reaction, okay? And that is formed because in the formation of this bond, a molecule of water is lost. Then we go again to the partial structure of polymer D. Okay, looking at the question, the polymer can be determined by the type of bond linkage, right? The monomer unit is actually an amino acid. Then in figure 6, right, the type of polymer is a polyalkene. The type of reaction is an addition reaction. All right, so figure 6 shows us here partial structure of polymer D. And this is actually just a polymer. This type of polymer is a polyalkene, right? And with alkenes, the type of polymerization is addition. All right, last question. We're almost there. Thank you guys for those who are staying with us for so long. So here we have question 6. Chlorine bleach can be used to prepare emergency drinking water supplies in times of natural disaster when pipe-borne water is unavailable. It is made by mixing chlorine and sodium hydroxide, caustic soda, in a kind of reversal of the chloralkali process. All right, now we want to state one physical property and one chemical property of chlorine. Now for the physical property, so physical and chemical, right? What can we see? Physical. It is actually a yellow-green gas. Yellow-green gas. Now, it reacts with metals to form metal chlorides, right? So reacts with metals to form metal chlorides. So the example here would be, so example, aluminum chloride, AlCl3. All right, describe a simple laboratory test that can be used to determine the presence of chloride gas. Simple. We're going to test with moist blue litmus paper and chlorine gas. Chloride gas is going to change the blue litmus paper to red, and then it bleaches it. All right, so litmus test. All right, so moist blue litmus paper, and then the chlorine turns blue litmus paper to red, then it bleaches it. All right, what are two other uses for chlorine gas other than that of purifying drinking water? So one of them is making insecticide. So the making of insecticide, guys, and it is used as a solvent, and it's also involved in the paper making process. All right, CFCs, all right, are organic compounds used as refrigerants and propellants in spray cans for deodorants, paints, and insect repellents, and are known to be harmful to the environment. So BI says state the meaning of the term CFCs, right? So the meaning is chlorofluorocarbons. So chlorofluorocarbons. And give an example of a CFC and state its formula. So that's 2 marks there, so give the worded. So we have chlorofluoromethane. So that's where the carbon part comes in. And this chemical formula for it would be CF2Cl2. Let me just make that a bit closer. So CF2Cl2. There we go. Question 3. Give the name and the formula of a molecule with CFCs react in the environment, right? And that is O3. And what is O3, guys? That is ozone. All right, guys, let us move on to the last question. And it says that we must describe a process by which the use of CFCs result in a harmful effect on the environment. And they are broken down by UV radiation in the upper atmosphere, which releases chlorine radicals, which further react with and deplete the ozone. Now, no ozone means that there's going to be no protection from the harmful rays. Things that can be affected are like plant proteins. They get easily affected by UV radiation, right? Which leads to the harmful mutation of cells, right? I don't know if you guys have ever looked under a microscope with chloroplasts, or in the chloroplast cells. See if I remember it correctly. I remember the chloroplast, or the chlorine molecules, or the chloroplasts, they try and move around in the cell, right? The chloroplasts move around in the plant cell, right? If too much sunlight is hitting the chloroplast, sometimes the chloroplast will be seen moving to another side of the cell so as to protect it from damage, okay? And also, it also increases evaporation of surface water through the stomata of the leaves and decreases the moisture content of the soil. Okay, and that brings us to the end of today's video. Now, this video, it may be a Resit paper, but it can still be used to prepare for May, June exams same way. Now, with that said, be sure to like, subscribe, and comment, and let me know if the video helped. That is it.